Hi class, welcome back. Last week we had a very brief introduction to SEM, structural equation modeling. I had an example to show you that we use SEM to evaluate proposed causal relationships in a linear equation system. The key here is to understand that the causal process is theory-driven, and the SEM takes a confirmatory approach to verify whether the proposed causal relationships are supported by the data. The first thing of today is for us to learn the notation systems that has been used in SEM. First, we need to know that the reason we need a notation systems like this is because the hypotheses in SEM are no longer expressed as mathematical equations or some type of statement like we did in ANOVA or multiple regression, like mu1 equals mu2 equals mu3. Those are not used here. The hypotheses are presented as a diagram, graph that shows the relationship between factors and variables. So this will be the system you're going to use when you present your diagram. If you have latent factors in your model, so you need to use the oval shape to represent the latent factors. For observed variables, you use the rectangular shape to represent them. If you took a measurement course before, you would know that the observed scores is made of two components. It doesn't matter what you are measuring. A big chunk of the observed value should be the true score, the true characteristic you are trying to quantify. In addition to that, there are always some type of errors. The error could be random errors, and there could be some systematic errors. In the SEM diagram, we actually do not differentiate between random or systematic errors. They together are expressed as an E in the diagram. Similarly, for latent factors, there is an unexplained variance that is called disturbance in SEM. We are going to explain this in more details in the future, but right now the information I can give you that the disturbance is the part of variance in endogenous factors that cannot be explained by the exogenous factors. Here, the exogenous is quite similar to the word independent in the context of multiple regression. So endogenous is the dependent factors. So the disturbance of latent factors, they are expressed using the letter D in the diagram. Before we move on to example, I just want to have a brief mention of this JKW system. They are the people who first invented SEM as a statistical procedure. So they have their own system that has been obsolete at this point because they use Greek alphabet, and that's sometimes it's not only confusing, it's intimating to people. So this type of elements, the factors, the variables, and the error and disturbance, they need to be connected some way in the diagram. Here are the type of connections you will encounter in SEM diagrams. The first one, a straight line with arrowhead at the end. It's called the hypothesis structural effect. It represents the causal relationships between variables or between latent factors. The second type is the so-called non-directional relationships is hypothesized between variables when they have covariations or correlations. You use this kind of non-directional line to represent covariation when you cannot specify based on the information you have which variables cause and which ones effect. The third type of line here is a curved line that's represent the correlation or covariance between the two or more exogenous variables or factors. The last type of curve, the lines with two arrowheads at both ends, pointing to the same variables or factor. This type of line represents the variance of exogenous element. The words element here just represents either a variable, measured variable, or a latent factor. Now we are ready for example. Okay, in this diagram we have 5 latent factors. They were placed in oval shapes. For each of the latent factors, we have observed variables or measured variables as the indicators. For example, for achievement motivation, the first latent factor, F1, we have 2 observed variables. They are in this rectangular shape, and we have motivation variable 1, motivation variable 2, and for each of the measured, what I call them observed variables, there is an error component. Okay, so you can see the error to variable 1, error to variable 2, and so on and so forth. The primary research interest of the study are shown here using those structural relationships here. You can see that achievement motivation is hypothesized to have a direct impact on job satisfaction. So does verbal intelligence. Self-esteem have an impact on job satisfaction, but it's indirect, and the impact is mediated by this factor that's called performance. Here, achievement motivation, self-esteem, and verbal intelligence are all exogenous factors. Job satisfaction is an endogenous factor. Performance could be an endogenous factor if you are looking at the relationship between self-esteem and performance. In the meantime, it could be an exogenous factor because it has direct impact on job satisfaction, the endogenous factor. So you can treat performance as locally endogenous and locally exogenous. Remember that for endogenous factors, we have to specify disturbance, the unexplained variance based on the proposed model. So we have disturbance for factor 4, disturbance for factor 5. Now pay attention to here. We have covariance between the 3 exogenous factors, which means based on the theory or based on some type of empirical evidence, we believe there is correlation between achievement motivation and self-esteem, between self-esteem and verbal intelligence, also between achievement motivation and verbal intelligence. That's why those 3 curved lines here to show their covariance. Okay, the last point I want to make here is about the observed variables. Remember the observed scores, each of them is made of 2 components. The true score is from the underlying factor. And there's some error. Both the true score and the error contribute to the observed scores. That's why you see the error pointing to the observed variable from the error as well as from the latent factor, the underlying cause. Our second example here is a pass model, the model without any latent factors. So you can see that both the exogenous and the endogenous elements, they are observed variables, okay? And you have the curve that starts and ends at the same variable that represent the variance of this observed variable. Since there's no latent factors, we have error, not disturbance. We have error for the endogenous variables. This type of model we see here is unstandardized model because you can see the variance for the exogenous variable, and you can also see the variance of the error component of the endogenous variables. In addition, you see this is the covariance, not a correlation between the two variables. When you have an unstandardized model, the pass coefficient are labeled with letter B. The numbers in the subscript represent from which variable they start, at which variable they end. So B for 1 is the pass coefficient that pointing to V4, start from V1. Keep this unstandardized model in mind. Let's move on to a standardized version of this model for comparison. So in a standardized model, we still have the same 4 observed variables, but since it's standardized, the variables all have a variance of 1. Okay, so you do not have the little curve that start and end at the same variable to represent the variance, because we know they all have a value of 1. Between the two exogenous factors, there is a correlation. The correlation is labeled with R, no longer covariance. And the structural relationship here, they are represented by the line with an arrowhead at the end. Their values are called pass coefficients. The standardized pass coefficients are labeled with letter P, the little letter P. The numbers in the subscript have the same meaning. So P for 1 means it's the pass coefficient ends at variable 4 and start at variable 1. Finally, for the two endogenous variables, V3 and V4, we know they have a variance of 1 in standardized model. So for the error component, it's 1 minus what can be explained by the structural relationship. So we do not need to estimate the variance of the error component. Alright, so hopefully this will help you to understand the models, the diagrams in the future.